Okay, so here's a Zoom meeting for Physics 231C. We're in the end of the second week of October, so here's the Zoom meeting. We've been studying chapter 7, which is on oscillations, and the reading quiz for chapter 7 is due the end of today, Friday the 13th, and then the big problem set is due Monday night. When you read the chapter, you should take notes and make sure you understand and have written down the important equations. So here are the sort of equations that you'll see in chapter 7. First of all, there's a section on periodic motion, and there's a relation between frequency and period of oscillation. Then there's the special case of simple harmonic motion. That's periodic motion where there's a definite frequency. So the function, let's say the position as a function of time, will be sinusoidal. A good example of simple harmonic motion is a system with a mass and a spring. So a mass is attached to one end of the spring, the other end of the spring is attached to a wall. Then the angular frequency, omega, is the square root of k over m, where k is Hooke's constant for the spring, and m is the mass. That's angular frequency, so that's radians per second. It's related to the frequency. Frequency is just 1 over seconds by a factor 2 pi. So here's the period of a mass and spring system. There's a section on energy in simple harmonic motion. For example, again, in the mass and spring system, there'll be two kinds of energy: kinetic energy of the mass and potential energy of the spring. And we've studied kinetic and potential energy before. The kinetic energy is a half mv squared, and the potential energy is a half kx squared. X is the displacement from the equilibrium. Now, if we have an oscillation with amplitude A and frequency omega, or angular frequency omega, then we could look at the energy at the equilibrium point. At the equilibrium point, the potential energy is 0. That's x equals 0. And the velocity will be a omega, either plus or minus a omega. So the kinetic energy will be 1/2 m omega squared a squared. And at that particular point in the oscillation, all of the energy is in the form of kinetic energy. But then as the object oscillates, there'll come a time when the kinetic energy is 0. That's when it reaches its maximum amplitude. And so then the energy is just 1/2 Ka squared. All of the energy is in the form of kinetic energy. These two energies are the same because energy is a constant. So, the energy is sloshing back and forth between kinetic energy and potential energy, but the total amount is always the same. It's just distributed differently between kinetic and potential. And there'll be a time when all of the energy is kinetic energy, there'll be another time, half a cycle later, where, or a quarter of a cycle later, where all of the energy is potential energy. And this gives you a way to relate velocity or speed and displacement, because this quantity is a constant. So I can solve for V. Take E minus a half kx squared. E is a half ka squared, so I can take it as a half ka squared minus x squared divided by 2, multiplied by 2, divided by m, take the square root. So conservation of energy is a useful concept to use when you're dealing with harmonic oscillation, any kind of oscillation, but in particular, simple harmonic motion. There's a section which shows the relationship between simple harmonic motion and uniform circular motion. If you project circular motion onto one plane, you get harmonic motion. There's a section on the pendulum. A pendulum's another example of an oscillation. When the amplitude of oscillations is small, the period of oscillation is 2 pi squared of L over G, where L is the length of the pendulum and G is the acceleration due to gravity. It's gravity which is causing the bob of the pendulum to swing back and forth, because the gravitational force of the Earth is always pulling it down. So that'll cause it to oscillate back and forth between some maximum angle and some negative of that maximum angle. Now, this has the interesting property that the period does not depend on the amplitude. L is not the amplitude. L is the length of the pendulum. The amplitude is how far it's swinging back and forth. The amplitude might be considered the maximum angle. Well, for small angle oscillations, the period doesn't depend on how far it's swinging. So if it's swinging over very small angles, it'll be moving very slowly. If it's swinging over larger angles, it'll be moving more rapidly. But overall, the period will be the same in both cases. And then finally, the most difficult, most advanced section in chapter 7 is on damped oscillations and driven oscillations. And a damped oscillator, there's a formula in the book for the position as a function of time. It's not just a cosine omega t oscillation form, it's also multiplied by an exponential factor, e to the minus bt over 2m. So in other words, it has an oscillation, but the amplitude decreases exponentially in time. So you end up with damped oscillations. We'll see some examples of that in some problems. Now I'm going to have to leave promptly at 4:45, so let me go ahead right now and show some examples, give some hints for some problems in the assignment. So here's a case of oscillations of a molecule. And we'll take as an example the carbon dioxide molecule. So this is in the homework assignment, and it's problem 44 in chapter 7. Now, a carbon dioxide molecule has this form. It's one carbon atom and 2 oxygen atoms, and it's a linear shape. So you've got the carbon atom in the middle and the 2 oxygen atoms on both sides. And it's just a straight line form. Now that's the equilibrium, but it can oscillate. So you can have various kinds of oscillations. You could have, for example, you could have the carbon atom oscillating up and down, or in this act, in the plus or minus y direction, and the oxygen atoms oscillating in the plus or minus x direction. That would be one kind of oscillation. But that's not the oscillation we're going to consider in this problem. we're going to consider the oscillation mode in which the carbon atom does not move. And each of the oxygen atoms move in simple harmonic motion, but in opposite directions. So the center of mass of this three-particle system is always the center, is fixed. It'll be just at the center of the carbon atom. So the carbon atom is at rest, the oxygen atom is oscillating back and forth in a plus or minus x direction. The other oxygen atom will be oscillating forth and back, 180 degrees out of phase. Well, since the carbon atom doesn't move, it's just the same as if as far as the spring is concerned, we'll treat the force between the two atoms as a spring. As far as the spring is concerned, it's just the same as if the carbon atom were fixed on a wall, were nailed to a wall, and the oxygen atom was oscillating back and forth from the wall. The other oxygen atom doing the same. So the frequency would just be the same as for one oxygen atom attached to a spring and the other end of the oxygen atom attached to a wall. So that's where the angular frequency is the square root of k over m. In this case, the mass m is just the mass of the oscillating part, the mass of the oxygen atom. K is the spring constant, which we're using to describe the interatomic force. Now, omega is angular frequency. Frequency, F, is omega divided by 2 pi radians. So one period of oscillation is 1 over the frequency. It's 2 pi radians divided by the angular frequency. So, there are various questions that can be asked here. This has to calculate the oscillation frequency. Well, oscillation frequency is 1 over 2 pi squared of k over m. So you have to put in a value for k, that'll be given in the problem. What's the mass of our oxygen atom? It's 16 Daltons, 16 atomic mass units. One atomic mass unit is 1.66 times 10 to the minus 27 kilograms. So it's a very tiny number in terms of engineering units. And then the frequency will be the square root of k over m times 1 over 2 pi. The unit will be 1 over seconds. That unit is given a special name. That unit is given the name Hertz, named after Heinrich Hertz. And you'll find that that's in the infrared. This sort of explains why carbon dioxide is responsible for global warming, because this molecule, not really by this mode of oscillation, but by a different mode of oscillation, where the oxygens move to the right and the carbon moves to the left, and vice versa. So that's where the carbon is oscillating. Then they'll be oscillating out of phase, and you can get absorption of infrared light, but it's the same it's a similar frequency. All right, so let's see. There's a question on the meeting chat. Do we set our calculators for radians or degrees? When in doubt, when in doubt, radians. When in doubt, use radians. And if it, whenever you write cosine theta, and theta is omega t in this case, cosine omega t, omega is angular frequency, so that's radians per second. T is time. So omega times t will be radians. And so your calculator for calculating cosine or sine should be set in radian modes. But I would say that for almost all problems involving oscillations, you'll want the trigonometric functions as a function of radians. And, unless you're doing trigonometry, that's about the only time you would want your calculator set in degrees. Unless you're doing trigonometry. We're not doing any trigonometry here. We're just doing motion. So unless you're doing trigonometry, probably you want radians. Here's another problem. This problem is for the pendulum. You have a pendulum called a simple pendulum if it's just a single mass hanging from a string, swinging back and forth. So in all physics problems, the first step is to draw a picture. So here's a picture. The mass M is swinging back and forth. It's moving on a circle because the length of the string is constant. That's the radius of the circle. So there's that relationship between circular motion and angular motion, which is quite visible in the case of the pendulum. Usually when we consider a pendulum, we use the angle as the coordinate. So you would express the behavior of the motion in terms of theta. What it says here is you pull the pendulum to the side to some maximum angle, theta max, and then you let it go, and it'll swing back and forth from theta max to minus theta max and back to plus theta max and back to minus theta max. It'll swing back and forth between a maximum value of the angle and the negative of that value of the angle. Now you're supposed to calculate the energy and the maximum speed. Well, energy is conserved, so you can calculate the energy at any time. The energy will be the same at all times. So we could calculate the energy when the mass is at its highest altitude or highest point. When theta is equal to theta max, let's call this direction y. Then the potential energy will be mgy. And I guess this distance would be y0. So the energy will just be the initial value of the energy because it never changes. It'll just be mg times the initial height, which is y0. Well, we're given the initial height in terms of theta max, so we would want to convert from theta max to y0. There's a relation between y and theta, which in general is y is L times L minus L cosine theta, because, this distance is L, the length of the string. This distance is L times the cosine of theta, because by trigonometry, this is the adjacent to the angle theta. So if I take L minus L cosine theta, I get this little distance, which is the height above the equilibrium point. So in particular, y0 is L minus L cosine theta max. Now, you also may want to use this relation for any value of theta to relate theta to y, because y determines the potential energy. In particular, if you want to look at the bottom of the swing, that's where the speed will be the maximum. The kinetic energy will be 1/2 mv max squared. The potential energy will be 0 because you're at the bottom of its motion. We call that ground level. So U is 0, K is a half mv squared at the equilibrium point, that has to be, so this kinetic energy has to be the energy, the same as the initial energy. So you can solve this equation for V max. You just multiply by 2, divide by m, replace K by the initial value because U is 0 there. So V max is the square root of 2e over m. So part A is just to calculate the total mechanical energy. Well, that'll just be the potential energy when the bob is at its maximum angle. And then part B is to calculate V max. Well, V max will just be the square root of 2e over m. And you calculated E in part A. So you just put that into the value of E, and that'll give you V max. So you see, it's quite easy to go back and forth between the maximum height of a pendulum and the maximum speed it has. The maximum height occurs when the bob is at rest instantaneously, and there's no kinetic energy. The maximum speed occurs when the bob is down here at ground level, where it doesn't have any potential energy. Okay, let's go on to this problem, which is a little bit different. It's problem 54 in chapter 7. There's a piston which is oscillating up and down harmonically. You could arrange that like this shows. It's attached to a rotating, say, a disc with some kind of design, so that as the disc rotates, the piston goes up and down. And again, there's this relationship between uniform circular motion and harmonic motion. So the up and down of the piston, that's the harmonic motion. The circular motion is here. So the coin, which is sitting on top of the piston, not attached to the piston, but just sitting there, will undergo simple harmonic motion. In other words, if I again call this the y direction, then the coin, assuming it stays in contact with the piston, is just going up and down. As a function of time, its coordinate will be a cosine omega t. Omega t I can write as 2 pi times the frequency, because omega is the angular frequency. Now, you have to read section 7.4. If this is the coordinate, then the acceleration is given by this equation. I mean, if I know the coordinate as a function of time, I can write down the velocity as a function of time. That'll also be sinusoidal, but it won't be a cosine, it'll be minus the sine. You know, you should have those equations written down from reading the chapter. And similarly, if the velocity is sinusoidal, then the acceleration will also be sinusoidal. But it won't be cosine, it'll be negative cosine. And it'll be multiplied by the angular frequency squared so that it has the right units. A will be meters. Omega is 1 over time, so this will be meters per second squared. Now there's also radians in there, but radian doesn't really have a dimension. It's just a number. It's just a plain number. So I would have here omega would again be 2 pi f squared. All right, so that's explained in equation 7.11 and in figure 7.11. So we know, we're asking, will the coin remain on the piston? Now you can sort of visualize in your mind's eye, if the piston's going very fast, it'll bounce the coin clear off. If the piston's moving too fast, the coin won't remain in contact with the piston. It'll just fly off when the piston reaches its highest point and then starts back down again. The coin won't remain in contact with it. If the coin is going to come off the piston, it'll happen at the top. At the top is when y is equal to a, the maximum height, the amplitude, and ay is minus a omega squared. Now, by Newton's second law, the mass times the acceleration will be the force. And there'll be two forces on the coin. The coin will experience the force of gravity, which is minus mg, negative because it's downward. And it'll also experience the contact force with the piston. We just call that F contact. Now, if the coin doesn't fly off the piston, then the contact force has to be a number greater than 0. So in order for the coin to remain in contact with the piston, we have to have F contact greater than 0 at the top. If F contact were equal to 0, that would mean that the coin is not in contact with the piston anymore. So that contact force has to be greater than 0. So that means that let's see, the contact force is equal to mg plus ma. So here's the contact force. That's mg plus ma. Or that's mg minus ma omega squared, because a is minus a omega squared at the top. At the very tippy top, it's accelerating downwards if it's still in contact. Well, let's put it this way. The top of the piston is accelerating downward. Its velocity is instantaneously 0, but it's accelerating downward because it's going to start going back down again. Anyway, that has to be greater than 0, so that gives you a maximum value of the amplitude. The amplitude has to be, move this to the other side of the greater than sign, divide through by m omega squared. A has to be less than mg over m omega squared. And that'll be the maximum value of A. If this is moving very fast, or if it's moving very far, very long distances, the coin will come flying off the piston. So, you've got this condition. You know what omega is because you know what F is. Omega is 2 pi F. So you plug in, you know what G is. G is a universal constant. So you can immediately cancel how large can the amplitude be? What's the maximum possible value without the coin flying off the top? Okay, any other questions? I don't see any questions on the meeting chat. I'm going to have to leave and end the meeting pretty soon, but I have one more example. Here's another example. This is an example of damped oscillations. Now, damped oscillations are a little more difficult to analyze because they involve both a sinusoidal function and an exponential function. So when you have a damped oscillation, the position as a function of time is some initial amplitude. So A is a constant. A doesn't depend on time. A would be the initial displacement from equilibrium. But now the amplitude will decay exponentially. So damped oscillations are an example of exponential decay. And then there's still oscillating part, at least if the damping is small, which we can represent by a cosine function, cosine omega t. And omega depends on the spring constant and the damping constant and the mass. You know, if there were no damping, B would be 0. And then omega would be the square root of K over M. Just a mass on a spring. But if there's damping, omega is a little less than the square root of K over M. So again, that's in the chapter. Make sure you have these equations written down. Here's the picture. I should have shown the picture first. A mass is attached to a spring sliding on a horizontal surface and decaying. For example, there would be some friction here with the floor. Or there would be friction with the air, even if the floor were made of ice. So there were no friction at all with the floor, the mass would be moving in the air, and that would give you damping from interacting with the air, you know, transferring energy to the air. Air would be set into motion. So we have, you know, an immovable wall and a floor and a mass with some equilibrium attached to a spring with an equilibrium length. So this has an equilibrium length, some L, L0 for equilibrium, and a Hooke's constant K. Then the force is minus Kx, that's Hooke's law, which we saw in an earlier chapter, minus B times V. So that's the velocity dependent frictional force. You know, the faster it's moving, the larger the frictional force will be. And it's in the direction of negative V. So in other words, if the mass is moving to the right, friction is pulling it back to the left. Friction always acts opposite to the direction of motion, because it's sliding on the, well, let's think of air resistance. It's moving through the air to the right. The air is kind of holding it back, creating a force to the left. So here's the form of a force with damping. Minus Kx is the restoring force of the spring, depends on the spring constant. Minus BV is the force from friction. Now in the problem, you see we're given M, we're given K. Here's M. Here's M. Here's K. We're not given B. So we're going to have to find an equation which depends on B. That's what we're supposed to figure out. So that's the problem. The problem is to determine B. The information we're given is that the amplitude decreases by 50% in 12 periods. Now the period is 2 pi over omega. So the period is 2 pi over square root of K over M minus B squared over 4M squared. And now 12 periods would be oh yeah, 12t. Yeah, here it is. So here's the time dependence. It's the exponential minus bt over 2m. The unknown is b. We're trying to figure out b. The time we're given is 12 periods. Let's call the period of oscillation t. So set the time equal to 12t. And now The amplitude at that time is 50% of the original amplitude, which was A. So the amplitude is A exponential minus B times 12t over 2m. The amplitude is the quantity that multiplies the cosine. And that's supposed to be A over 2. So those are the equations. You know, in every physics problem, we start by drawing a picture like this, writing down the necessary equations like this, and then coming up with a formula. And the formula is going to be this 1/2 is the exponential minus b times 12t over 2m. So 1/2 is the exponential of minus b over 2m times 12, and t is 2 pi over omega. We're supposed to solve for b. What makes this problem difficult is that b itself depends on, or rather omega, which appears here, this omega also depends on b. So the b dependence here is kind of has two parts. It's got this factor of b, and it's also got a factor of b in here. So you're going to have to go through some algebra to pull out the value of b, which is the question. Now you have this equation. One thing to do is to get rid of the exponential function by taking the log, the natural log of both sides of the equations. Natural log, you have a natural log button on your calculator, is the inverse of the exponential function. So the natural log of 1/2, which would be the same as negative the log of 2, is the natural log of the exponential of this quantity. Well, the natural log of the exponential of x is x, because natural log is the inverse of exponential. So if you think back to high school algebra where you studied logarithms, when we take the log of the exponential, we just get the quantity which is inside the exponential, which will be this minus, I guess 1 power of 2 will cancel, minus 12 pi b over m squared of k over m minus b squared over 4m squared. Okay, so now we've got the equation down to something which doesn't involve the exponential function. Of course, we have to calculate the log of 2, but you have that in your calculator. So this is something you know. Now, you know, it's just algebra at this point. Multiply both sides of the equation by this square root, then square both sides of the equation. When you square 12 pi b, you'll get 12 pi b squared. You'll have the log of 2 squared. You'll have minus 1 squared, but that's just 1. You'll have, we could bring this m inside the square root, then I'd have km minus b squared over 4. So when I square that, I'll get, km minus b squared over 4. Mk minus b squared over 4 on the right-hand side, this on the left-hand side. And now I just have a linear equation for b. So I can solve for b squared, take the square root of that, that's b. So you see this is a good example of kind of a usual approach to a physics problem. You draw a picture and label it with the various parameters that you're going to use. Then you write down the equations. Then you apply algebra to solve those equations for the unknown. The unknown in this problem is b. In this case, there's a fair amount of algebra to go through, but in the end, it's, you know, each step is a small step. So finally you get b. So that's all I really had prepared for today. I have to leave pretty quick. Any questions? You could either put a question on the chat, or you could just unmute your microphone and speak up. Well, if there aren't any questions, then I will mute the microphone. I will stop the recording.